Welcome back. So now we're going to start talking about select properties of liquids. In particular, we want to spend some time talking about surface tension, viscosity, and capillary action. So let's do that. Surface tension is basically the resistance of a liquid to increase in the surface area. Okay? So it doesn't want to spread out and increase its surface area. It takes a certain amount of energy in order to pull it apart. And that unit is going to be Newton meters. That's the amount of energy divided by meters squared. Okay? And if we see at the surface, this is basically gas phase. This is basically your liquid. I have all these forces when I'm on the inside of my liquid, holding it on my liquid particles, my liquid molecules, in this case water. But at the surface, I have fewer interactions. But the surface tension is all of the attractive forces between my water molecules that hold them in and prevent them from going into the gas phase. Okay? And I'll show you some more examples, but let me just tell you, how can you float a paperclip on the surface of water? And that is because when you put the paperclip very carefully, if you put it in vertically, it'll just sink. But if you float a medium or small paperclip, don't get a large one because that's too heavy, okay, it will float on the surface of the water. And that's because the amount of downward force, where I'm trying to spread this out, it's distributed so that I can't break my surface tension. Is less than the amount of force needed to pull these apart. Okay, so where do we see it besides just trying to float paper clips on the surface of water? Water striders. These are I like these bugs. Okay, so next time you go to a pond, you gotta check these guys out. And you can see that why does it dipple? Because they're heavy enough they push down on the surface of the water. But because it's distributed enough, what happens is when they push down, it's not strong enough to break apart the forces that hold the water molecules together. And that's why they stay on the surface of it. Likewise, when you look at the water droplets, see these water droplets? On the surface, I have surface tension. And so there's a competition between breaking this, like that's when your water falls apart and splats on the ground, versus holding it in. And so you've got two forces together, and it's kind of like the same thing with water bubbles. The surface tension on the surface, those interactions are holding all your molecules together at the surface, and that is being in competition with actually spreading out so much that the inside water molecules can actually spread out. Okay. What about other properties of liquids? There's one called viscosity. Viscosity is the measure of resistance to gradual deformation by shear stress or tensile stress. So when you're pouring your liquid, basically it's got to flow past each other. And so that's the shear that we're talking about. Essentially, another term is the thickness of a liquid. The thicker it is, the more viscous. Okay? So, if it pours very quickly in a certain amount of time, it's considered a liquid of low viscosity. An example would be water. If it takes a long time for that same liquid to pour, then it's considered a highly viscous liquid. Example that people like to invoke is honey. So honey versus water. Okay, so what are the units? Centipoise, okay, or 1 millipascal seconds. So remember, time's involved because we need to see how long it takes to actually pour a liquid. Okay, so very low viscosity liquids are like water, okay, acetone, all right? You have gases. as you go into liquids, as you continue to increase in viscosity, you get to paste and they look more like solids. I mean, look at toothpaste. Has a 300,000 centipoise. All right, a very highly viscous substance. And look at ketchup. Ketchup's highly viscous. Okay, and fondue. So next time you go and have a nice fondue party, okay, you know, you can be standing there doing a cheese fondue and talk about what the viscosity is of the fondue. It'll make a very good party conversation. Okay. What other properties are we going to talk about? We're going to talk about capillary action. And capillary action describes the spontaneous rising of a liquid in a narrow tube. Okay, and the two forces involved in capillary action is a cohesive force, which is the attraction of the molecules within itself, and the adhesive force, which is the attraction between molecules of a liquid with the walls of the container. Okay, so let's take a look. So, all in blue, see this? These are my liquid molecules, right? All in blue, these are all of the cohesive forces holding my liquid together. All the red, where I'm interacting between my liquid and the side of my container, the substrate, those are called adhesive forces. Okay? So, let's take a look. Capillary action. So when I'm going to back this up so you can see a little better. These are all open to the air, so it's all the same pressure. So why is it that with a thick, large diameter tube, the liquid is much lower than the very narrow capillary tube, which goes to about here? Okay? So with water, the adhesive forces are greater than the cohesive forces. So when I have a narrow tube, I can actually go up higher, trying to increase the adhesive force of attraction, and so this will compensate in terms of being so light, the gravity that's pulling it down. Whereas when it's thick, large diameter, there's not a lot of adhesion because basically it's just this small area right there, okay, before it becomes too massive to climb any higher. All right, so how can you tell? If you look at your meniscus and it's smiling, a happy one, okay, your adhesive forces are greater than your cohesive forces, but you're trying to maximize how much surface you can rise up on. Okay, so like water, you can see that when we read it, we always read at the bottom of the meniscus, but it's a happy meniscus. So we know adhesive forces is greater than cohesive forces. It wants to maximize how much contact it has with the glass. On the other hand, mercury, you can see that it's a sad, convex type of meniscus. When it's that type of convex meniscus, it's got capillary repulsion. It wants to minimize contact with the glass surface. We know that the adhesive forces are less than my cohesive forces. Okay, so next time you go to a barometer and you're looking at the mercury, you'll see when the mercury rises, it has a very convex appearance. Whereas when we're reading a burette for, let's say, acid-base titration, you'll see it's concave. So my adhesive forces is greater. Okay, so let's take a break here and then we'll come back and talk about vaporization and vapor pressure.